Welcome. I'm K6TD. Thank you very much to AA7A Ned for getting this organized and going and did most of the slide work for us. We've got two good radio presentations for you. One about the rib, which I think most of you have seen and used or heard about, and then Gregg created the not the micro rib as I call it, the next generation rib, which has a different application. And finally, Bill's going to talk about the thing everybody came to hear about MOAS. So with that, I'm going to turn it over to George. Go ahead.
Thanks, Kevin. When we originally started to think about rib-type DXpeditions, really the first thing was, can you go back just for a short time to the other one? Obviously, we wanted to break the deadlock that we had with Fish and Wildlife Service. Basically, the Baker Island DXpedition turned them off, DXpeditions. And we said, okay, a light footprint with DXpedition that doesn't involve camping should be really the way to break the logjam. And indeed it did. We're now working on the third DXpedition where exclusively it was the rib that allowed us to get a permit or get around the permit. And so the concept works. It's not without issues, but obviously nothing is perfect. The next slide. The architecture we decided to use is built around the Flex radios, specifically the Flex 6700, and to some extent the new 6000 or 8600 series. And these radios appeal to us because of two things. One is that they, of course, are very easily networked, they're IP-based radios. And the other one is that there's two ways to run the radio, either with software, Smart SDR, or a Maestro remote console, which makes it feel exactly like you were running a local radio. The link that we run to the ribs is a 900 megahertz link. It's about 30 megabits per second or something. And the latency on that is less than 30 milliseconds. So it really feels like you had the radio right next to you. And the architecture is, it's pretty simple. Depending on the version, we have a version with two radios and 100 watt output, or a single radio with an amplifier, which puts out a kilowatt. But in both cases, the architecture is very similar. Ethernet switch that connects the radios to the bridge, and then a separate what we call DAC, which provides the internal monitoring controls, antenna tuner control, etc. A bunch of functions there. We do have a PC in the rib, but most of the time we just use that for local troubleshooting. So when we go out to the island, we use that PC to do some troubleshooting. These are just small little laptops. And the most important part of the rib, apart from the actual radio, is the filters. The places where we go very often have either limited space or just simply, it's only 2 or 3 of us that set up all the stations and antennas. We cannot deal with, 1,000-foot cables and antennas scattered all over a large area. So the antennas are quite close to each other, and interstation interference is a big issue, and therefore all these ribs have filters, bandpass filters in them, and we try to always have a bandpass filter. It's really a must. We have another rib that we recently developed, which is not shown here. Oh yeah, it's here, this one. This rib is a new rib we call P-rib. It's in a much smaller, lighter case, and it has two 100-watt radios and an external amplifier and an external filter. And these are just in some small Pelican cases, and we're proven to be pretty reliable at on N5J or on Jarvis. This is really the future as far as we're concerned, because the weight is less than half of this, and it's much more portable, much easier to handle. And this is what we're going to take to St. Paul, St. Peter rocks, because there the challenge is getting the equipment from the tender onto the dock. Last time I was there, we had 6-foot surge. That is, the tender was going up and down 6 foot every 6-7 seconds. And you just had to hand things over as quickly as you could. So these portable ribs will be the right solution for that. The big issue with a rib that's designed for total remote control is it has to be weather-tight, 100% weather-tight. In fact, these things are watertight to the point that I think if we dropped it in the water for a short time, we wouldn't have a problem with them. The challenge with that is that you need to cool it, and for that really water cooling, liquid cooling is the only practical method, because you have to remove a kilowatt of heat. And that water cooling is probably the secret sauce in making a rib that is weather-tight, and it runs cool no matter what. It's out in the sun or wherever it is, it runs cool all the time. And it's not shown here, but on some of the pictures you can see we have these external radiators that are used to get rid of the heat. This diagram shows the boat end. What we have on the boat end is for the local stations, Maestro consoles, and for the remote stations we have PCs. And whether we have a Maestro or not, we always have a companion PC that goes with it. The PC has the control software, and as well as logging, etc. So it's really, you have a Maestro, a laptop for logging, but that also has the control and monitoring software, because we're dealing in these ribs with 1 kilowatt amplifiers, and you really have to watch what you're doing when you have a kilowatt amplifier feeding a antenna that is controlled by an antenna tuner. These tuners can detune or whatever. Lots of things can go wrong, and while with 100 watts nothing happens, if you go into a high SWR thing with a kilowatt, you have to be a little bit more careful. But this is really the boat end. So each station has a Maestro and a corresponding laptop, and they connect it through a switch. And what is not shown here, oh yeah, it's shown here, is a router other than the Starlink router. For years we were struggling with the Starlink routers, and what it turned out, we had all these strange dropouts, that the radios would drop out and we would have to reconnect them. And we found out that the Starlink router would reassign the addresses, and everything would drop out and you have to reconnect. We put a separate router in, and that one made the whole thing stable. Like on Jarvis, during the 2-week period, we maybe had to reset 2 or 3 times the radio, not more. So the dropouts were not an issue, and that's because of this particular router. We used what's called a Firewaller, and that turned out to be a very good router, really good router. And then basically this is the configuration we had on Jarvis. And what you can see, the remote radios that we had, they were running on them AnyDesk software. And the AnyDesk software allowed the remote to basically remotely operate the smart SDR radio software that was on the laptop. Now, separately, we had Mumble for the audio delivery, and W1V, we'll talk about that at another time. That's a science of its own. Just getting the audio back to the operator it's not simple. FT8, of course, is dead simple, because you just have a screen and you just click, 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 and it does all the work. I mean, I say 4 times simpler, 5 times simpler. Do we have more slides on this? Yeah. This is a diagram of a particular the more detailed configuration of the P-rib. As you can see, the box has 2 radios, a control deck with a PC. But as I said, the PC really is just there for local testing. And one thing about a rib operation is that the rib is out on the island, and you are on the boat. Anything goes wrong, you have to go out to the island. So you don't want to be carrying gear with you. So we just put a laptop. These are $300 second-hand laptops from eBay. And we just put it in, it's permanently, and it's powered from DC. So we can use that laptop for local troubleshooting, test the radio, test the tuners, etc. And then with this is, I think, a very interesting amplifier. On the Jarvis, we ran it at 500 watts, and it's designed to be totally automatic. That is, if it has a fault, it will reset. So, if, for example, if you have a high SWR and it shuts down, when next time you try it, it will reset and try again. If there's a problem, it will shut down again. But you never have to go to standby and switch it back to operate, because it's too hard for the remote operator. That's not a joke. And again, with this amplifier, an external bandpass filter. Again, if you ever plan a DXpedition, bring the bandpass filters. You need bandpass filters. You will not survive without them.
That's it on slides. Yeah. George, thank you very much. Next is the micro rib, or the next gen rib as it's better known.
So the genesis of this really started on Magnet in 2023. Can you hear me? Thought about taking the technology that George developed into a little bit different direction, a little bit different packaging. Next slide. So our goals in the design objectives were long-term high availability. And when we're talking long-term, we're talking in terms of months, not weeks or days. We wanted to make this product stable enough and suitable for unattended operation. And we felt that that was a real high bar, and anything else we do with complementing a traditional DXpedition would just fall into place. It's designed for hands-off operation. It's our belief that if you were to get a DXpedition to take this box with them, they need to set it up, connect the coax, connect the internet, connect the power, and let the remote team operate it. And to get there, we've implemented a comprehensive set of remote management capabilities. And then we've also done some integration with Starlink, where we can control the Starlink terminal from the RIB control console. So it's lightweight. It fits in a 3RU case. We started off with K3s. Actually, I started off with a Yaesu FTD-X10, real great, nice internet-enabled radio, but it weighed too much. It was really heavy. And so I had a K3 sitting on the shelf, and we hooked up a K3 to a Raspberry Pi and used it as a TCP server and started to play with it, and kind of came to the conclusion that this was the direction we wanted to proceed. And it fits in an overhead on an airplane. It is lightweight, weighs about 30 pounds. One person can carry it. And these were all objectives that we set forward with when we started to design this. So it fits in a gator box. A gator box, it's sitting right down here. Clamshell front and back panel. We looked for a rack shelf to use, but we had to fabricate our own because we couldn't find one that fit our needs. Most rack shelves are steel and rather heavy. We started off with K3, and we were well on the, in the planning process for Rotuma, and the idea was floated to fit a K4 in the box. And it's a pretty tight fit, and we got a K4 in August of last year, and I think we had it ready to ship in 2 weeks. Ready to ship hardware-wise. We didn't have any software for it, but we shipped it anyway. But there's a long story behind that. And by the time we got to Rotuma, the software was ready, and we uploaded the software to it, and everything was just fine. Small form factor, a little hockey puck. It's a Ryzen 7 PC now, and it runs all your FT8 software, WSJT or MSHV, N1MM, and also the Win4 K4 software, which gives us a dashboard. The Raspberry Pi 3 is a supervisor. It monitors all of the other network-attached devices in the RIB for health status. The small router, like George, we ditched the Starlink router. It's too big, too bulky, and it doesn't do some fundamental things that a consumer-grade router should do, like DHCP reservation, that sort of thing, and dealing out addresses randomly. We built a custom DC distribution charge controller because we learned that we needed to have a backup battery that would carry over the RIB in the event of loss of AC power. And so the battery solution we have, it can run just the networking equipment. It can power the radio at 100 watts, or it can power the radio at reduced power. It's all user configurable. Back to the power supply, one of the things we experienced on Rotuma was brownouts. And so the power supplies we were using had switchable input ranges, which doesn't work. So the Meanwell supply's got a broad range input of 90 volts to 280 volts. So it'll survive a brownout. We were seeing our 240 volts service on Rotuma was dropping down to about 145 volts at times. So it was a little bit flaky. So we've designed around some of those issues. Next slide. Okay, so we talked about the, okay, sorry, no worries. Talked about the first bullet. So one of the things we found as far as wanting to get to hands-off is there's a number of ways we needed to handle monitoring of the various subsystems, the PC, the router, and Starlink. So the Pi sends a ping to the PC. If the PC stops responding, we send a wake on LAN packet, which is a magic packet that's supposed to turn it on. If that doesn't turn it on, we power cycle the PC, send a magic packet, it comes back. Same thing with the router. We power cycle the router if it loses pings. And monitoring the cat traffic, this goes back to the K3, is we massage the cat traffic into a heartbeat that Node-RED monitors. Loss of cat traffic, we power cycle the radio. We said, well, with the K4, why don't we just ping the radio? And you could do that, it's real easy to do, but we felt that there could be situations where the small board computer in the K4 could be up and running, but maybe there was a problem with the application software running on top of it. So we felt that monitoring the cat traffic was still the way to go. And we do the same thing with Starlink. We ping Google DNS, and if it goes away, we wait a minute or so. It doesn't come back, then we power cycle the Starlink. And then we log everything using MQTT. So even if the RIB is offline, we've got a log of what happened, even though we don't have connectivity at that point in time. And then the logs from the RIB are sent up to a server in the cloud as well. Like George, we use, when we're on a beach somewhere, we use the same antenna setup with a remote tuner. These antennas work really well. One person can put up the antenna and have the RIB on the air easily within an hour. And we're using MFJ remote tuners. We're working on another tuner because obviously the MFJ tuners are unobtainium at this point, so we need to come up with another solution for that, and we've got a good start on that project as well. One of the things that we're really keen on is automation as much as possible. It's difficult when you're a remote op and you have to go in and hit split and A equals B and all this. So with our tuners, we operate them automatically. When a band change or a mode change, which involves an excursion in the band, is detected, the internal tuner is bypassed. We send a low-level RF signal to the external tuner. It tunes. We drop the RF signal. We turn the internal tuner back on, and we tune it. So the result is you always have a flat match. And it doesn't require any operator intervention. When you change modes, and I'll show you on the desktop in a little bit, go on CW, just enter the frequency in N1MM. You hit the CW button. It normalizes the VFOs, sets the radio to split, and sets the receive VFO up 1. Does the same thing on sideband, except it sets it up 5. So the operator doesn't have to go through all that rigmarole of moving VFOs around. The filters are all normalized to the proper bandwidths for the mode. Same thing with FT8. You hit the FT8 button, it sets the filters to the data, disables split, and it's just kind of a one-touch macro that puts the radio into the right mode. If you had somebody that's buggering around with stuff, pushing buttons, I call moving the furniture around, you can hit this button and it brings everything back to normal. So we use a two-desktop approach. This is the CW screen. We actually ended up having to write our own browser. We were using a browser from a company called Calibri in Australia. One day they stopped support and it stopped working. So the guy who does the software work for us, he wrote this browser. We like to monitor temperature. Temperature kind of tells you what's going on in a hurry. So we monitor the temperature of the K4, temperature of the Pi, temperature of the PC. If any temperature exceeds a threshold, it turns on the fans in the rib. Other than that, the fans don't run. Because the fans don't run, all you're doing is moving dirt around if it's not needed, and it's just wears out the fans quicker. We use sticky notes on the desktop to provide instructions for the operator. So if the operator comes on and says, hey, I forgot how to do this, he's got the instructions right there on the desktop for him. Next. So this is the FT8 screen, and you just push a button at any desk and you toggle from one screen to the other. It works real well. You have the same dashboard view into the rib, know what's going on. So like George uses, we use AnyDesk. We decided after our last trip that we wanted to have some sort of access control, because right now if you have the free version of AnyDesk, if somebody has the password and the number to get in the AnyDesk code, they can get on. So in the commercial version, AnyDesk is implemented a whitelist ACL, so we're going to use that. It gives us another layer of control. The remote ops collaborate in real time on Slack. And one of the things that really surprised me is our first outing to Juan Fernandez was that the dialogue, in the Slack channel was just like you would have if you were sitting in a tent on a DXpedition. They're talking about pileups, rates, conditions, propagation, what band they're going to go on when they're in the chair. And we had a sort of a post-trip debrief, and a couple of the guys said, this was the most exciting experience I've had in ham radio. So it really got me passionate about this, that we were able to put this together and folks were really enjoying it. So we're putting together a dashboard for the remote users, which is going to have status of all the radios on the expedition, because you need to know where to go. If you jump on and the band's dead, you need to know where the other stations are at. And we actually have 3 modes that the rib is in. It's going to show online or offline. Offline would be, say, if Starlink was down, or a maintenance mode. Remotely or locally on the island, you put the K4 into test mode, and it lights up a maintenance light on the user panel. And this tells the user that the radio is being worked on by somebody. And gamifying, I picked up this term. There was a podcast on W1DED's deal, and Craig Thompson, K9CT, used this, and I go, that's a great way of characterizing this. So we're going to leverage the work done by Kyle AA0Z to put together a comprehensive dashboard that shows queues, mode, rate, and come up with a score mechanism so that these off-island operators actually have something to get on and motivates them to make as many queues as possible. And just basically creating a competitive environment for it. And we think that's going to be something that's going to be really enjoyable for the remote ops. One more, Kev?
Next one is you.
Okay, well, that's it. And it's Bill's turn. And take it, Bill.
Go for it, Bill.
All right. Hey, everybody. So I'm here to talk to you about the MOAS project, something that K1XM built a few years ago and how we've been using it at some of the various contest stations that I operate at. Just a little bit about me. I've been licensed for, call it 26 years, but I only really kind of came active in 2017. I primarily operate at ZF1A and ND7K, but I try to help as many people as I can and operate in anywhere that I can. Only a couple contests a year. I'm still working, and I'm active in all three modes. So I actually did a presentation about this a couple of years ago here at Visalia, and I talked about primarily in-band contesting and sort of how we implemented at some of this contestation. So this is sort of a subset of that. The problem that the MOAS primarily solves for us is if I have a large number of transmit antenna switches, receive antenna switches, stack matches, or amplifiers, and I need to sort of use all of these things in coordinated fashion. I mean, it really, the thing about all these devices, they have very similar interfaces. So generally, it's either a key line or add 12 volts to energize a relay coil times, several hundred of these in a typical contest station, sometimes several thousand. And there's a lot of permutations of antennas and just various things that have to be true in order for a given radio to get an RF signal out on a given antenna or set of antennas. And I need a single box that can coordinate all of that without two radios trying to take the same antenna or various other bad things that can happen. But also a lot of contest rules have limitations like you have to have, you can only have one signal active on a band at a time, so you can't have two signals active on the same band at the same time. So the mother of all switches box is something that helps me do all of those things. And it also just happens that, at one of these stations, we don't always do the same categories. So in some cases, we have to go between, a single op configuration versus a multi-single or multi-two or multi-multi. And what we expect the interlocking behavior to be and how we're using the various radios may change from contest to contest. And it would be really nice if we didn't have to rewire every time, all of our automation every single time. So just to quickly explain how sort of the most simple version of run and in-band may work. So you'll have one person on a run radio who's CQing and answering calls. And many modern radios have the capability of taking the transmit antenna and actually looping it out to the RX out port. And then it expects that to come right back in on a receive in port. And what you typically use that for is to share the transmit antenna between two radios, and as long as one of the radios, the primary radio isn't transmitting, that loop out occurs. And in the other point, we might want the in-band radio to be able to listen on any number of receive antennas. So this is just sort of a very simple view of how that might be connected. But this only scales so far. If you have a couple of antennas, then I wouldn't necessarily encourage you to go down the MOAS route because it can be somewhat complicated. But when you have 12 receive antennas or multiple four squares or multiple beverages that can switch directions or end fire arrays or any of these different systems where you might have a large number of antennas that you have to worry about, some automation is going to be necessary. So here's a box from low band systems. I actually have heard that you can get these through some. I know they're made in Russia, but you actually can get them shipped here through some convoluted paths. I don't believe K9AY is making his receive switches anymore, but I have heard of a couple of those still being used. And then there's also OK2ZAW from Remote QTH makes a couple of these large receive matrix boxes. But typically what we've done is we've used one of these receive antenna arrays, and we've used a PCB that Marty and N1C and I sort of put together, and our MOAS to do some interesting things with this switching. So first of all, this is sort of our most simple setup. So basically we have either one or two amplifiers, and basically when both radios are on the same band, we're going to share a single amplifier. So what we're going to do is when the run radio transmits, it'll go through its own amplifier. And if the in-band radio wants to transmit, and they both can't transmit at the same time, keep in mind, we'll use a transfer switch to move them through the run and in-band amplifier. And we have to make sure that the key lines are appropriately routed to the right amplifier. But if, for example, we need the run radio and the in-band radio to be on different bands, we'll actually have the in-band radio key up the mold amplifier and use it on a different band, and we have to just make sure the key line's routed, to that amplifier when it's in use in that particular configuration. So the box that ties this all together is the MOAS, and basically you can sort of, when we say mother of all switches, it's actually not even a switch, it's a giant relay driver, and what it does is it energizes pins on these various devices in the shack, and by default it has 64 different outputs as well as PTT inputs, and inhibit outputs are so that you can signal to the radio that they shouldn't transmit or receive. And essentially what we're doing is, again, keying the right amplifier, engaging the transfer switches, engaging the various other systems that we have, and we can enforce very complex rules like this radio takes precedence over this one, and so forth, right? We can implement any of these with just configuration files, essentially. And what's nice is that between contests or between operators or between whatever we're trying to do, we can entirely change its personality if we need to. Any questions?
Thank you very much. Mr. Question? Ned's going to go first, but okay. Go ahead, Ned. Oh, he wants the microphone.
Yeah, that's Ned, A7A. Bill, to configure that MOAS, do you have to write HTML, or is there a tool that helps you create the code for that?
Yeah, there's no tool. You use a text editor, and it's not HTML, it's JSON, JavaScript Object Notation. And you generally write very big files to do this. You have to read Paul's manual, and it takes a good afternoon to make a good working MOAS file. You need to test it out and so forth. But if you're ever looking for a template, we have, between NN1C and I, we've tried and broken it in possibly every way. So I'm happy to help anybody with that.
Another question back there?
Gregg,
Yeah.
is
Jim.
the next-gen rib, is it the same thing as that coffin-size rib that we started with?
No.
Is that right?
I mean, same capabilities?
No.
Okay.
They're designed for a completely different set of applications. Good idea. Thank you, Ned. Appreciate that. They're designed for a completely set of applications. George's, why don't you talk about your application set and I'll talk about mine.
So the rib that we built is designed to be outdoors, totally weatherproof. As I said, we could probably even drop it in the water. It would be fine. The whole idea with that is that there's nobody on the island. There's nobody around the equipment. And so it's a weather-tight, remotely controlled station.
And in contrast, our rib is built to complement a traditional DXpedition, and it's also been now used to support getting more young folks involved in DXpeditioning, which is working out really well. I'll talk more about that tomorrow. But again, we've designed it to be high availability for a long period of time. For instance, you leave your station PC on for 2 months, you might want to restart it. Same kind of thing here. PC could lock up. We have the ability to restart the PC either by trying to wake it up with a LAN or by power cycling it. So 2 distinctly different sets of applications. They're both in boxes made by the same company, and I guess that's about where the commonality stops.
Right, of course, there's a lot in common. What I wanted to add to what Gregg said, think of it as a pre-assembled station.
Yes.
And at a DXpedition, that's a big issue because traditionally you have radios, cables, power supplies, all these things. And if you've ever been on a DXpedition where they're putting the gear together, you hear, where are the coax cables? Where is this? Where is that? How come this plug doesn't fit? Whatever. That doesn't happen because it's all pre-assembled, and you basically just add power on one end and plug the antenna on the other end, and the Ethernet cable, and that's it.
Yeah, one of the young hams coming to Saba with us last week told me he wants to do exactly that. The local stations are all going to be ribs, and I have to build another rib now because we're going to have 3 local stations, but it's just that. It's Ethernet, power, coax, you're on the air.
Well,
Other questions? We're running low on, yep, right in front here.
Hello, C1 Romeo Hotel. Okay, you've got the microphone, thank you. Palo C1 Romeo Hotel, I noticed on one of the first ribs you had an external 500 watt linear and a bandpass filter after that, and even a multiband antenna for that bandpass filter. How do you where do you get the bandpass filter that carries multibands with 500 watts?
I'm not sure I understand the question.
So we have a non-resident antenna that has to be tuned.
Okay, yeah.
And the bandpass filter matching up to it.
Yeah, so
Repeat it.
if you notice on the diagram, these antennas have antenna couplers or antenna tuners with them. These are automatic antenna tuners. We send like 10 watts of power and they match the antenna to the coax. And then once we turn on the power, we lock these tuners by supplying them a different voltage. So go back one more slide, please. Yeah, sorry.
The problem was a 500 watt.
A bit more. Yeah, here. So here you see the external amplifier and the bandpass filter. Sorry, right here. So the system works in a way that these tuners have a control board in them that detects the power supply voltage. So we send 12 volt, and at 12 volts the tuner is locked. And when we want to tune, we send 15 volts to the tuner, and that 15 volts is detected and it unlocks the tuner. So when the amplifier is in the standby mode, we can tune up the antenna. When we have a good SWR, we lock it by sending a 12 volt power supply signal, and that tuner is locked, and then we get as a good match. The bandpass filter essentially is just transparent on that band, and this is a fairly unique amplifier that we build. It uses a single LDMOS BLF189 transistor, and it puts out about 900 watts, 800 to 900 watts. Also on the Jarvis, we had it throttled down to 500 watts because this was a remotely operated station, and I just simply didn't trust the operators with more power. But this worked more or less flawlessly, except some issues with the secondary station antenna tuner retuning. And that's probably an important subject, that the tuners that are generally available have this automatic tuning function, which is cool, except every now and then they automatically retune. And if you're running an amplifier, that's a big no-no. So that's why we use this voltage-controlled tune lock mode.
But the bandpass filter is capable of carrying 500 watts?
The bandpass filter is a kilowatt bandpass filter.
Yes.
It's built into a Pelican case.
Okay,
And
so
it's
home built bandpass filter.
Yeah.
Okay.
The whole, in this rib, there's a lot of home build. The amplifier, same thing with these things. The amplifier is home built. The bandpass filter is home built. The DAC is home built. You just have to do it because there's nothing commercially available that would fit. And especially, all these amplifiers are water cooled. There's no other way to do this but with water cooling.
Answer your question okay? Next question. Are we running low on questions? Oh, there's a gentleman to your, on the other side, Kyle.
Brian, W7JET. So have you guys given any thoughts, or is there like, this is pie in the sky kind of thing, but incorporating, eventually making these usable with like an ROV, rather than having to actually move them on the shore with a boat, but incorporating ROV technology into flying it in? I'm a pilot, so I kind of think about things like that.
That's a separate project.
I figured I wasn't the only person thinking about that, but I specifically thinking about Bouvet, I'm like, that would have been a heck of a lot easier to move it over to the shore that way.
Not a joke.
Yeah.
We had a small prototype running in the pool the other day. But for a different application, not ham radio.
Other questions? Okay, we enjoyed your time. Thank you very much. Hope you learned a little bit about your